Am I audible? Um, yeah, if I'm audible, I'll start off. Yeah, and I hope the screen is visible as well. Yeah, cool. Hi guys. I'm Arjun. I'm from the Department of Electrical Engineering in IIT Madras, and today I'll be taking a session on decision trees. Um, Decision tree is a very popular machine learning algorithm, and it is widely used to perform a variety of tasks, such as classification and regression. So, before further ado, let's start the session. So, what is a decision tree? The formal definition is that it's a supervised learning algorithm. As I mentioned, it's a machine learning algorithm, and I'm sure you guys are familiar with supervised and unsupervised. In supervised, we have labeled data. So this algorithm works on labeled data, and it's used for classification and regression, as I mentioned earlier. And uh, as is clear from the name, it has a hierarchical tree structure which consists of multiple parts, which include root node, branches, internal nodes, decision nodes, leaf nodes, etc. We'll go into the detail of the structure later. So, what exactly is a decision tree? So far, it's we just learned a formal definition of it. So, in simpler words, a decision tree is basically consists of a bunch of if-else statements. Since we already had a session on Python, I'm pretty sure you guys are familiar with what an if-else statement is. So at each point, we ask a question, we ask ourselves a question, we make a statement, and then make a decision based on whether or not the statement is true or false. So yeah, so this tree can be divided into a bunch of nested if-else statements. It'll be made more clear if we take a simple example. Yeah, so this will explain things, this will make it more clearer. So, this simple decision tree is used to classify if a person is fit or not. The very first question we ask ourselves is the person aged less than 30 or more than 30? This is the very first statement, the if-else statement. And if this is true, we ask another question, if a person eats a lot of pizzas or not. And if that is true, then he's classified as unfit. So basically, through these set of questions, we can classify if a person is fit or unfit. And in the very first question, uh, if it was false, then we ask another question, if he exercises in the morning or not. And if he does, then he's considered fit. If not, he's unfit. So this is the a very simple decision tree, and it makes things a lot clearer, because so far I've just given the formal definition and I've mentioned it is only theoretical. This will improve your understanding on decision trees. So um, yeah, this is the given example is called a classification tree, as it classifies the data set into the people into fit and unfit. As I had already mentioned, decision trees can also be used to predict numerical values, and they are known as regression trees. We can look at the same example here. Instead of predicting if a person is fit or not, we can predict the weight range or the weight of a person. So, based we can ask more questions based on relating to his height and yeah, again, his food eating habits. And then after we ask a bunch of questions, we can finally find out the weight range or even the exact weight of a person. So that is uh, a decision tree for a regression task, that is to find numerical values, predicting numerical values. Here, the decision tree is for classifying if the person is fit or not. So it can be used to perform both classification and regression, which makes it a very useful machine learning algorithm. In our session here, we'll be mainly focusing on decision trees. And before we build one from scratch, I just need to tell that by convention, whenever the statement is true, we go to the left. here, if it's true, we go to the left. If it's false, we go to the right. That is the convention I'll be using from now. So when in the trees I built further, we will not be having any ticks, crosses, true or false. It's just left and right. So you guys must be familiar with that. So just keep a note of this. Yeah, moving ahead. So as I said, we'll be building a decision tree from scratch for a particular data set. And before we do so, we have to go through a few important terminologies relating to our decision tree. So this itself is a decision tree, and the different parts are mentioned here. The topmost part of a decision tree is called the root node. Uh, and the blue colored ones are called the internal nodes or the decision nodes. So even the root node is a decision node because we are making a decision. We are moving either left or right based on the statement, that is based on if the statement is true or false. So all these are decision nodes. So these decision nodes can be split further, and this splitting continues until we reach this node, which is called a leaf node. A leaf node cannot be split further. So if I go back to this is a leaf node. Once we finally classify if the person is fit or unfit, there is no need to ask further questions to classify it into any other type or divide the node further. So yeah, this is a leaf node, and this cannot be divided further. So overall, just to recap, this is a root node, and these are the decision nodes or the internal nodes, and this is the leaf node. Just a recap of whatever I taught you guys. The top of the tree is the root node. The subsequent nodes are known as internal nodes or decision nodes. And finally, we have the leaf nodes. Also, when we make a split, this decision node with respect to this is called its left child, and this is called its right child. Same for this. This is the left child of this, the right child of this. That is another terminology. So yeah, so now that we are familiar with the major terms related to decision trees, we'll move ahead to building one from scratch. We'll be using a very simple data set, and our objective is here is to predict if a person loves Red Bull or not. So that we do that using some of the likes and dislikes of the person, and these are known as the features, and this is the target. So the target is to predict if a person loves Red Bull or not using these features. And yeah, the three features are loves fruit juice, loves soda, and age. And based on this, we'll be predicting if a person loves Red Bull or not. So before we start building the tree, the very first question we need to ask ourselves is what should be at the top of the tree? That is, what should be the root node? Uh, Here we have multiple features. So we can choose any one of them to start off. Like we can either start off with loves fruit juice as the first feature or the first statement or the root node, or we can use love soda or age. So let's look at how well loves fruit juice and love soda predicts if a person loves Red Bull or not. Yeah. So um, if we start off with loves fruit juice. Of all the people who love fruit juice, three of them don't like Red Bull. One person likes Red Bull. And of all the people who don't like fruit juice, two of them like Red Bull. One doesn't like Red Bull. And yeah, just a reminder, as I mentioned, the convention here is if this is true, we move to the left. If not, we move to the right. And if we use love soda as the root node, out of all the people who love soda, three of them love Red Bull and one person doesn't. And interestingly, all the people who don't love soda, they also don't like Red Bull. So here, if you observe, this one node is different from all the other nodes because it contains people of only one class, that is, people who don't like Red Bull. So if we use love soda as our basis to classify or as basis to split or the feature, we get one particular node which cannot be split further because this contains only people who don't like Red Bull. Although both of them, like, they don't perform, they're not able to completely split the data set directly into people who love Red Bull or not. We can see that Love Soda here does a better job than Love's fruit juice. That'll be made clear in the further slides. Yeah, as I had already mentioned, from the looks of it, neither of the two trees do a perfect job in predicting if a person likes Red Bull or not. But again, as I had mentioned, these three leaves are different from this because these three contain a mixture of people that love or don't like Red Bull. But here, it only contains people who don't like Red Bull. So such leaves, which only contains people belong to one class, are called pure leaves. And the if you recollect, it can also be called a leaf node here because it cannot be split further. So these are pure leaves or pure nodes, and the remaining three are impure nodes. Yeah, that is clear here. These three are the impure nodes because it contains a mixture of people, and this is a pure node because it only contains people who don't like Red Bull. So moving on, now that we have started off with our root node, we only considered Love's fruit juice and Love's soda as a criteria for splitting. Um, we completely forgot about age, and we'll be taking that into consideration in some time. So far we've just had an intuitive understanding of uh, which feature performs a better split. That is, we told that Love Soda would be a better way to start off our tree. That is better root node. But this is just an intuitive understanding because we get a pure node. It'll be better if we get a numerical value of this purity impurity stuff, and that can be done using two ways. One is using something called Gini impurity, and the other one is using something called information gain and entropy. So since the second tree performs better, it uh, mathematically it should have less Gini impurity. So it'll make more sense if we quantify this impurity, and then you guys will be more clear. In while building our tree, we'll be using Gini impurity and not entropy, and I'll be covering entropy later. Gini impurity being the more popular one, we'll be using that to build our tree. Yeah, also, before we move on further, this is the QR code link for the very first Slido question. Uh, if you're able to access the question, just let us know if you're able to view it or not, and I'll share the quiz. Is it visible? Are you guys able to access the Slido question? Yeah, I think quite a few are able to do it. So quite a few have voted, around 105, and the Unfortunately, the majority of votes is to the wrong question, wrong answer. The answer is this. But yeah, I hope my screen is visible. I'll stop the Slido quiz now. Also, before I move further, I'll just explain why that is the right answer. Um, I hope everything is visible. So the question was, which of the following is not true for a decision tree? So it cannot be used in data mining application as it only classifies but does not predict anything. In the very first slide, I had mentioned that it can be used for both classification and regression tasks. So here, data mining application refers to regression tasks and predicting numerical values. So that means that is the only statement which is not true about decision trees. So I'll move on. I'm hoping this is visible. Yeah. So as I had mentioned, we spoke about impurity, purity, etc. And it'll be better if you're able to quantify this and find a numerical value of what this purity impurity actually means, and that can be done using something called Gini impurity. The formula for Gini impurity is given by 1 minus summation of pi square, where pi is a proportion of ith class label. So you can also put it in another way. Suppose you have you have data points and you choose one particular data point, and the pi here is the probability that it belongs to the ith class label, the data point. So yeah, the Gini index is given by just the summation of pi square, and the Gini impurity is given by 1 minus summation of 1 minus summation pi square, which is 1 minus the Gini index. Again, I'm repeating, pi is the proportion or the probability of the ith class label. It'll be made more clear using our example by what a class label is and so on. So in our case, the Gini impurity is 1 minus probability of Vs square minus probability of no square. What is probability of Vs square? Probability that a person likes Red Bull or doesn't, and probability of no is the probability that he doesn't like Red Bull. So we can use this to find the Gini impurity of every leaf node, every node. When we split something based on a particular feature, to find the Gini impurity of the split, we have to take the weighted average of the individual Gini impurities. It'll be clear if I perform the calculation on our own decision tree which we started off. So we had the confusion between loves fruit juice or loves soda, which one should be at the top of the tree. So if you use loves fruit juice as our feature, we get, if we based on the split, we get these two nodes. If we calculate the Gini impurity, the Gini impurity of this is 1 minus a square minus probability of no square, that is 1 minus 1 by 1 plus 3 whole square minus 3 by 1 plus 3 whole square. And for this node, it's 1 minus 2 by 1 plus 2 whole square minus 1 by 1 plus 2 whole square. And it makes sense also, because I'll tell you why it makes sense intuitively, why Gini impurity makes sense. The Gini impurity for the right leaf, that is here, is 0.444. I explained the calculation for that. And for left, it's 0.375. So, as I had mentioned here, to find the Gini impurity of this entire split, we have to take the weighted average. Weighted average is given by uh, the number of data points here divided by total data points, that is the weight of this node multiplied by the Gini impurity, plus again the weight of this node multiplied by its Gini impurity, which is 4 by 4 plus 3 into 0.375 plus 3 by 4 plus 3 into 0.444. These are the weights of these particular leaf nodes. And again, we get the weights through this 1 plus 3 by total number of data points, which is 7. 2 plus 1 by total number of data points, which is 7. Those are the two weights that will give the weighted average. So finally, when we perform the calculation, we get 0.405, which is the Gini impurity of this split. I'll just go through it again so that it's clear as to what Gini impurity is, because it's very important for all further calculation. So we perform the split, we calculate Gini impurity for these individual ones, and then find the weighted average. We multiply the Gini impurity values with its particular weights and then sum it up. This is the Gini impurity for the right leaf. This is for the left leaf. And the weighted average gives value of 0.405. So if you use Love's fruit juice as our criteria for classification, we get 0.405 as our Gini impurity value. Now, if you use Love's soda as our criteria for classification, if you perform similar class calculation, that is 1 minus 3 by 1 plus 3 whole square, etc., and then we find the weighted average, we get the Gini impurity for this node as 0.214. And it makes sense. Earlier we had I mentioned that this split gives us a pure node, or a leaf node, because this has only people belonging to one class, that is people who don't like Red Bull. So uh, also, this will also help us understand why Gini impurity makes sense intuitively. If you find the Gini impurity value of this, it is 1 minus 0 by 0 plus 3 whole square minus 3 by 0 plus 3 whole square, which is 1 minus 1, which is 0. So the Gini impurity value for this node is 0. That means it is a pure, it's a leaf node, it's a pure node. So that's why the Gini impurity overall for this split is less than the other one. So far, we only looked at Love's soda and Love's fruit juice as the criteria for classification. We have totally ignored age. Age is a little more complicated than those two because it consists of numerical values and not just yes or no data. So this, uh, just a second. Yeah, I hope I'm audible. So this contains numerical values, so it's not as straightforward as Love's fruit juice or Love's soda, because these are just yes or no values. So we can't just use any one of them to directly classify. So we perform a there's a very smart method to deal with this problem. We find the average age of uh, the consecutive cells here, and then we make another table, and we'll be using this as the feature to perform the split. So we can either use 9.5, 15, 26.5, so on till 66.5, any one of them to perform our very first split, that is to decide if this can be a good root node. Again, we find the Gini impurity values for all of these splits. I'll show an example. If you use age less than 9.5 as a criteria, people age less than 9.5, none of them like Red Bull, and people aged more than 9.5, three of them like Red Bull, three of them don't. And the Gini impurity value for this is 0, and it's pretty clear, it's a pure leaf. And for this, it's 1 minus 3 by 6 square minus 3 by 6 square, which is 0.5. So again, when we find the weighted average, and I'm sure you guys understood what weighted average is. So this will give 0.429. So this is the Gini impurity for this split. If we perform the same thing for the other average ages, we just saw 9.5. If we do the same for 15, 26.5, etc., etc., we get these values of Gini impurity: 0.429, 343, and so on. From this table, our main objective is to reduce the impurity, right? So we have to take the age with the lowest Gini impurity, and here the lowest Gini impurity is 0.343. And earlier, when we calculated the Gini impurity for Love Soda, we found that the value was 0.214, which is less than this. So we'll be choose finally we have come to the conclusion that for Love Soda, the Gini impurity value is the least. So we are able to extract the maximum information out of that split. So we will be using that as a root node. So after all this calculation, we just found out what the root node is. So Love Soda is a root node. So if we perform the split, we get these two nodes, and this is a pure node, which is a leaf node. We don't have to perform the split again. And this is a very good split to start off, and we have also proved that mathematically. So now we have an impure node here. We have to again split it further to get leaf nodes finally. Finally, our objective is to classify if a person loves Red Bull or not. So here it again consists of a mixture of people. So we need to be sure. We need to get our leaf nodes, which is a pure node. So we again perform the same calculation by finding out the Gini impurity values, and this is a reduced data set, by the way, because we've already used Love Soda as our criteria for classification. This is the root node. So now this table only consists of people who love soda, because we are looking at this. People who love soda only consists of people who love soda. So now we have to decide which one of these two features to use to split it again. We can either use loves fruit juice or age. Again, we perform the same old calculation again of finding the Gini impurity values. We can do that for loves fruit juice and for the age. And we find the average ages: 12.5, 26.5, 36.5. Here, if you observe closely, if you use 12.5 as your age to classify, if you use 12.5 as our uh, you know criteria to classify, all the people aged less than 12.5 belong here, and they don't like Red Bull. All the people aged more than 12.5 belong here, and all of them like Red Bull. So this, using 12.5, we get two pure nodes, two leaf nodes. So the Gini impurity is 0. So this again, we can easily make out that this is the best split. We can also prove it by finding the Gini impurity for Love's fruit juice, that is performing this split, and then we find the Gini impurity individually and the weighted average, and we get that the value is 0.25. I'll show you why. This is a pure node, so the Gini impurity is 0. This has half yes, half no, so Gini impurity is 0.5. And then again we find the weighted average and we get 0.25, and this is more than 0. We got 0 for age 12.5. Also note that I've not performed calculation for 12.5, and because it's clear that people aged less than 12.5 don't like Red Bull. People aged more than 12.5, all of them like Red Bull. So that again, we can conclude that age 12.5 is the best criteria to choose to split this further, split this. So finally we get our tree. So we started off with a data set consisting of people who like Red Bull, who don't like Red Bull, and we had features love soda, loves fruit juice, and age. And we started off by you choosing love soda as a root node because it had the lowest Gini impurity. And if that was true, we moved to age less than 12.5. And if that was true, all of them don't like Red Bull. If that was false, people like Red Bull. And if this original question was false, none of them like Red Bull. So finally, we have built our decision tree, and all of these are the leaf nodes or the pure nodes because we cannot split it further. So while building a decision, while building your own decision tree, when you reach a particular point where you have only people belonging to one class and you know that you can't split it further, That is where you stop splitting and where you stop building the tree, and you know that the tree has been constructed. So yeah, so now this tree can be used to predict if a person likes Red Bull or not. So I'll show you why this does a good job. So you have a data, suppose you have a person who likes soda and is aged, say, 15. So he likes soda and he's aged 15. So he loves Red Bull. So given a new data point, or given a new person with some likes and dislikes and his age, we are effectively able to predict if he loves Red Bull or not using this. Yeah, this tree can be used to predict if a person likes Red Bull or not. As I mentioned, while building the tree, we used Gini impurity as our index to, you know, find the impurity values. But I had already mentioned that there are other ways, which include entropy and information gain. I didn't use that to build our tree. So I'll be explaining that with a simpler example and explain how it works. Entropy and information gain. So yeah, entropy, I'm pretty sure you guys are familiar with the thermodynamics entropy, which again is the same definition as this. It's a measure of disorder or impurity in a data set. More the number of, suppose you have a data set that consists of a wide variety of people with different likes and dislikes, then it has a lot of disorder. Suppose you have a data set which only consists of people who like one particular thing, then it is very ordered and it has low entropy value. And the formula for entropy is minus summation pi log pi. Here pi is the same pi we used for Gini impurity, which is the proportion of the ith class label, or the probability of the ith class label, or probability that a person belongs to the ith class. This is the formula. So I'll tell you why this again makes sense intuitively. Suppose you have a data set which only consists of people who like, say, Red Bull, in which again it'll be easier to understand. Then the probability of yes liking Red Bull is 1, and the probability of people who don't like Red Bull is 0 because it's a pure node. Then the entropy will be minus pi log pi, and ps is 1. So the and p no is 0. So log 1 is 0, and again if you use the second term, we get 0 into log of something, which the summation will be 0. Basically what it means that is the entropy value is 0 for a pure node, which is same as what we found out for Gini impurity. The Gini impurity value was 0 for a pure node or a leaf node. And it's obvious that the higher the impurity, the harder it is to draw conclusion. That is, the harder it is to find out if a person likes something or not. I mean, here is I'm saying likes because that is what I use. It can be any uh, target. So this is entropy. So now we look at information gain. Information gain measures the reduction in entropy. So our aim is to reduce entropy, right? Because we want to get purity in our data set. We want to achieve pure nodes or leaf nodes. So that is done using information gain. So the split which gives us the maximum information gain is the split we use to we use to build our tree. So it'll make more sense when I give the example. I'll just explain what I've written here. So information gain is E of S minus weighted average. E of S is the entropy of the original data set, and weighted average is the weighted average of the two entropy values of two nodes after you split. Earlier we found out the weighted average of Gini impurity. Here we find the weighted average of uh, entropy, and then subtract that from the original entropy value to see how much the entropy reduces at. So if you have a large reduction in entropy, we are achieving purity. So we don't want to split it further. So that is our main objective. So it will be more clear if I give you an example to explain. It's a very simple example, a very simple data set. It just consists of one feature, that is color, and one outcome, that is yes or no. It can be whatever it is, but yeah, it's just the outcome, yes or no. And our objective is to again predict if the outcome of the observation is yes or no. So the entropy value, the entropy formula was minus summation pi log pi. So the original data set is just this, the entire all the 10 observations that has six outcomes as yes and four outcomes as no. So if you find the entropy of this data set, it will be minus ps log ps minus pno log pno. So ps will be 6 by 6 plus 10. I mean 6 by 10. 6 by 6 plus 4. 10 is because it is the total number of observations. So 6 by 10 log 6 by 10 plus 4 by 10 log 4 by 10. And the entropy value here comes out to be 0.971. So the overall, the entropy value of the entire data set without splitting it is 0.971, which is a lot. It's a very high entropy value, which means that our data set consists of multiple classes. It's not very pure, it's very impure. So we have to split it using some feature. Let's try color. Let's see if it actually helps us gain information. I'm hoping it's clear till now. I'll be moving forward. Um, Now, if we split it based on color, we see that if the color is yellow, we can if the color is yellow, we split it to this part, and if it's red, we split it to this part. Again, so that is, I think you can visually imagine that this itself is a decision tree. You have the entire data set. You find out what its color is. If it's yellow, we move here. If it's red, we move here. And then again, we find out the individual entropy values. So that is given by the same old formula, minus ps log ps minus p no log p no. So here, four observations have color yellow, six observations have color red. And out of the four observations which have yellow, three of them like Red Bull. Three of them have outcome yes, and one of them have outcome no. And here, three of them have outcome yes, three of them have outcome no. So again, when we find out the entropy values for these two, we get this as 0.811 and 1. 1 is a very high entropy value because it contains half of the observations yes and the remaining half no. So it's very impure. So this split looks like it's not going to help much, because if you find the weighted average, the entropy value is 0.924. I'm pretty sure you guys are familiar with weighted average, as I've already taught you guys. So the information gain here is 0.971 minus 0.924, which is 0.047. I'm sorry, this is not minus 0.047, it's 0.047. So that is the information gain we get through this. So that means that when we perform our split, we are gaining a little bit of information. So it makes sense to split it based on its color. So that is all when it comes to entropy and information gain. Before we move further, I have another Slido question for you guys. Before the Slido question, I'll just show you the formula for information gain as a recap. It is initial entropy minus the weighted average. I'll move to the Slido question. I hope you guys are able to. Wait, I think I'll just I'll just present it directly. Yeah, I hope you guys are able to scan it and you can find the, yeah, you can answer the question. You have around 1 minute to answer. Yeah, when you guys answer, I'll just go through the chat to see if you guys had any doubts so far. Someone has asked if an information gain and Gini impurity give the same result. Yes, they do give the same result. In most of the cases, they do. As you can, like mathematically, they are not the same, so there will be certain differences. But in most of the cases, you can use either of them to classify your to classify and build your tree. uh, how low a value of information gain is good enough? It's in the question itself. It's information gain. You need it to be positive. So if it's negative, there is no gain. So there is no point using that as a feature to split it. So that answers your question, because the information gain value has to be positive. Weighted average calculation. Just a second. I'll show that after this poll is done. I don't see any new entries in the pool. I think I'll just show the result, and it's pretty obvious as well. Yeah, 0.61, that is the right answer as well. I know it's a bit confusing. People have chosen minus 0.61, but it's E before minus E split. E split is the weighted average. So it's 1 minus 0.39, which gives us 0.61. And for the weighted average explanation, I'll just stop sharing this and explain that to you. So what is a weighted average? Weighted average is you when you perform the split. I hope this is visible. Yeah, when you perform the split, you find the entropy values of these two individually. That is your two nodes. These two can here be considered as nodes because it contains yellow colored observations and red colored observations. So when you find out the entropy values, you get 0.811 and 0 and 1. This is the entropy for the individual splits. I mean, individual nodes. To find the entropy, the information gain, you need to find the weighted average of these two. Weighted average, you multiply this with a weight. Here, weight is 6 by 10 for red. Why 6 by 10? Because there are 10 observations and 6 of them are red. And there are, out of the 10 observations, 6 are red, 4 are yellow. So 4/10 of it is yellow, 6/10 of it is red. So that is the weight. And then you multiply that with the individual entropy values and you get your weighted average. I'm hoping it's clear now. If you have any questions, you can still ask, because I'll be moving to the code implementation now. Yeah, I don't think there are any more doubts. I'll move to the next part, which is the code implementation. Just a second. Yeah, I hope this is visible to you guys. If it's visible, please let me know. Yeah, so far we have looked at the theoretical aspects of decision trees, and we built one from scratch using GNM Radial information gain. Here we'll be using decision trees to classify our data set, which here is we'll be using a very popular data set called the iris data set. It consists of is the iris flower data set, and it has three varieties: setosa, virginica, and versicolor. So our objective is to classify if an iris flower is belongs to any one of these types. We'll build a decision tree from scratch. This is a very lengthy process. This involves a lot of code. I'll just be going through it. I'll just be going through the code and explaining it simply and explaining what each function does and what each class does. You can go through the code later on and you can dive deeper to understand it better. And the very first step is to import all the necessary libraries. Here I'll be using NumPys and Pandas. So our data set has four features: sepal length, sepal width, petal length, petal width. And our objective is to classify if a flower is one of these three: setosa, virginica, or versicolor. These are the three iris flowers. So these we have the column names list, and we make our data frame out of it. We have our CSV file, which is iris.csv. We read it using pandas, and then this is the first 10 rows of the data set. These are the four features, and this is the target. If we print the unique values of this last column, we get setosa, versicolor, virginica. These are the three unique values found, the three different types of iris flowers. So before we start building our decision tree, our data set contains some of these non-numeric values. These are text values. So we need to convert them into numerical values. That is done using something called encoding. And we can perform encoding using the a built-in one called we can use scikit-learn's library, and we import something called pre-processing. So from scikit-learn we import pre-processing, and then we transform our data set. So what it does here is this variety column, setosa, versicolor, and virginica uh, are given the values 0, 1, and 2. That is done using this bit of code. So when you find the unique values in the last column of our new data set, that is the transform data set, we get 0, 1, 2. 0 is for setosa, 1 is for versicolor, 2 is for virginica. And it's clear in the data set here. So now we'll be building our tree from scratch. This is a very lengthy process. So if you're not able to understand it now, it's perfectly fine. You can go back, you can look at the code. Most of whenever you try to build any tree from later on, if you try to build something on your own, you'll never be building something from scratch. You'll be using built-in libraries. This is just to improve your understanding, and you'll improve your coding skills as well. So building the tree from scratch, we have two main classes. One is the node class, and the other class is the decision tree classifier. This node class consists of all the values you want to store in a node. You want to find out the feature index, the threshold, left and right. What is left and right? As I had mentioned earlier, it's for accessing the left child and right child of the parent node. I'm sure you guys remember what a left child and right child is. So these are the multiple attributes of this class. That is for a decision node. For a leaf node, you don't have all these. You don't have to split it any further. So you only have the value, and this is the class of the leaf node. In the example I had given, the class can be person liking Red Bull or person not liking Red Bull. Finally, when you reach the leaf node. So this is the class node. I'm sure you guys are familiar with classes, attributes, objects, because you would have learned that in your introduction to Python lecture. So these are the attributes of this node class. And again, this decision node also stores the information gain, and I'll be using that later on to build our tree. So this is the most important class, and it's a huge class. It consists of a variety of methods. Uh, so the decision tree classifier class has the constructor, which has root, which initializes the root node, and it has two attributes called minimum sample split and maximum depth. So if a particular node has a minimum number of data points, you don't want to split it further. So that is the minimum sample split, and we've given that as 2. If you have 2 data points in a node, there's no point splitting it further. So that is the minimum sample split. And then you have the max depth. Max depth is how long the decision tree is, like how many splits. And the max depth we have given here as the default value as 2. So this is the constructor of this class. And you have a build tree method. So this is a recursive function. This uh, I'm hoping you guys know what recursion is. Recursion is you call the function again and again. So you have x and y, which are, you split the data set into features and target. X is the feature, y is the target, and then you iterate it. You perform iterations until the condition is met. That is the minimum sample split and the maximum depth. If it overshoots that condition, you stop splitting. So every time you obtain the best split and you find the information gain using we find the best split using the get best split function, which I will explain later. And then you calculate the information gain. So if your information gain is positive, you'll continue building the tree. If not, you go out of this loop. So we uh, find if the information gain is positive, then we build our left subtree and right subtree and return the node. That is, it returns the node, uh, this one. So yeah, so this function is to build our tree, and this again involves a lot of other function which I mentioned below. This is the get best split function. Here we get our best split by like here in the theory part I explained that we have to find out the gene impurity values or the information gain for different features, and then whichever gives the maximum information gain, then we use that as the best split. So here we loop through all the features in the feature. We have 4 features. We loop through all the features in the data set, and we split the data set using the split function, and then you find out the information gain values and you store it in current information gain. And then you again you do that for one feature index, you do that for another feature index, and then whichever feature gives you the maximum information gain, we choose that as the feature for splitting. So that maximum information gain is like the maximum information gain is equal to current information gain. So our maximum information gain is updated each time we loop through a feature. So this will return the best split, the most optimal split. Earlier we had used love soda, loves fruit juice, and we found out that love soda gave us the most optimum split. Similarly, we iterate through all the features. The features there were love soda and loves fruit juice. Here the features are sepal width, sepal length, etc. So we iterate through it, and then whichever gives the maximum information gain, that is the best split. Note that we use this get split function to build our tree as well. Here get split, here you have two functions which I'll be explaining again later, the split function and the information gain function. Also, if you guys feel that this is a lot of code to handle right now, you can always go back, go through this code, and you will be able to get a better understanding. Here I'm just explaining it in brief. So the split function splits our data set into data set left, data set right. Basically splits it into the two nodes. So if you have a original node, you split it into two nodes, left and right. And that is done using np.array. If you use the feature index, if it's say we are using sepal width, if sepal width is less than say 2 inches, you split the data set to data set left. If it's more than 2 inches, you split to right, and that in the 2 inches value is the threshold you give. and then you find the information gain of the split. Again, information gain you can find out using uh, entropy of parent minus the weighted average, and I've used that here as well. You can either use entropy or or Gini index, any one of them. You can here I've mentioned there's a mode option, mode argument. The default one is entropy. You can also use Gini index. So this function returns the information gain, and this will be using the entropy function and the Gini index function. Entropy function is just the same old formula which I've mentioned earlier, which is minus summation pi log pi, p class into log p class. So you perform the summation using a for loop, and you find the probability of the class using this length of the total number of points belonging to one class divided by total number of points. Again, we use Gini index for find this function here is returns the Gini index. Gini index is summation returns the Gini impurity. Sorry. So Gini index is a function which I mean it's the method to calculate impurity. So that is summation of pi square, which is summation of p class square. Again, the same iteration to perform the summation, and it returns 1 minus Gini index, which is a Gini impurity. And this is for calculating the leaf value. So suppose you reach a particular point beyond which you don't want to split. You reach the boundary conditions which I mentioned before. That is this minimum sample split and maximum depth. After this you stop. So the stopping conditions. Then to find out which class it belongs to, you use calculate leaf value. That returns the maximum, that is maximum of all the entries here. Suppose you have two entries as yes, one as no, the output will be yes. It returns the maximum of the total entries. And this is a very smart way to print our tree. I'll be showing how this works later on when we print our tree. This function is to print the tree after you after you build the entire tree. This is the fit function. This function is a simple function. It's just used to activate to start building a decision tree, because we already split our data set into x and y. This will concatenate those two, and then you start building the tree. This is very similar to the dot fit function, which is commonly used in most of the inbuilt models in scikit-learn. And this is to predict which class it belongs to. It returns the predictions. Yeah, sorry. This make prediction function returns the prediction. So these are the various functions which are involved in building a decision tree. Right now, it'll look very heavy. If you spend some time on this, it'll be a little more clear. So now that we have built our decision tree classifier, we can use it for our data set, the iris data set. So iris data set is stored in data. We split the data into the features and the target. The features are on only the all the columns except the last column, that is data.ilog colon comma colon minus one dot values gives all the columns before all the columns except the target column, and y is only the target column. That is that is if the flower belongs to any one of the types, that is virginica, versicolor, uh, and the other one. So now whatever data we obtained, what we split the data set, now we split it into training and testing. I'm sure you guys would have learned that in previous sessions, why we need to split our data set into train and test. We train it on our train data set and test if it works. So that is done using train test split from scikit-learn. You get x train, x test, y train, y test. Make sure you give the same order, and it splits it into test and train. And as 20% of the data set is test, and 80% is train. Now that we have our data set, we train it on a train data set. We train the model, and we print the tree. Yeah, the print tree function is used here. So this is how the tree appears. If you give some thought, it's very simple to visualize the tree that I showed earlier. That is the tree structure. Using this, you have the features, and then you have the threshold. Based on if it's true or false, you go to left, right, and this again gives the information gain values here of each node. So after you fit the tree, this is how the tree looks when you print it. So this splits it into left, right, and then further split it. And after 3 splits, we stop because we gave the maximum depth as 3. So after we split it 3 times, we stop. So now we test if the model works well or not on our test data set. So from scikit-learn.metrics, we import accuracy score to predict the accuracy. The accuracy here is 1, that is 100%. It is able to predict all the test data points correctly. Just a second. Yeah. So I'm hoping you guys have a a fair idea of how to build it from scratch. Obviously, it is a lot to take in right now. So the code has been shared. You can go through it, tinker with it, make some changes to see how it exactly works, print it out, and then you'll understand how to build it from scratch. So yeah, just to recap, you have the node class, the decision tree class, which has multiple functions, and using that we are able to train our model and then print the tree and find the accuracy of its predictions. So yeah, I'm done for now. I think I'll share the QR code for attendance. So just a second. So this is the attendance QR code. So you can scan it and give your attendance. And that's it for today in decision trees. Now Daniel will continue with ensemble methods. So please scan this QR code and fill your attendance. And let us know if you're able to fill it or not. Um, Janav, can you activate it? It's not accepting responses. See there. Yeah, it's working now. Then that's good. Some people say that it's working now, so just please try doing it again and you put your attendance. We'll give some time for it, around 2 to 3 minutes. Uh, it seems someone had asked what is the physical significance of Gini impurity. Gini impurity is a mathematical function that is used to find out how impure the node is. So it I don't know how it was derived, but people came up with the function, and it is clear that when the node is pure, the Gini impurity value is 0. When it's impure, it's the highest. You get the highest Gini impurity value. So that function is effectively able to provide a mathematical relationship and mathematically predict values for impurity. So higher the Gini impurity value, more impure the node is. That is the physical significance of Gini impurity. and that is why we use it for building our tree. If you guys have any questions, you can still ask before, because now the next half of the session will begin. Explain the significance of information gain. Information gain is again just another method to find out uh, suppose you perform a split, and if the two nodes, if the impurity of the two nodes are less than what it was earlier, then the information gain is positive, meaning when we perform the split, we are actually gaining information from the split. So suppose in the example I had given before, you had you had love soda, loves fruit juice, and if you use love soda, loves fruit juice to split the data set, you are able to gain more information about the target, that is if a person loves Red Bull or not. So that is why we use information gain. Does Gini impurity obey second law of thermodynamics? I actually have no idea about that. S is this in entropy we use E of S minus weighted average. S is the split. S means split, and child, I had already mentioned, left child, right child are the left and right nodes when you split it. Threshold value of feature is say, suppose you use age as a feature. We had found the average values of ages 12.5, 16, etc. And we used each one of them to split our data. So that is the threshold, the values we use to split it. And I am not very clear as to what high dimensional and low dimensional data is. Yeah, I think I'll stop sharing now. Both Gini impurity and entropy can be used. Gini impurity somehow is a more popular one, so we use that for our classification. You can use entropy as well. Both of them work fine. Uh, less number of features. Yeah, it actually works better for lower dimensional, that is less number of features. If you have more number of features, the depth of the tree becomes too much, so it leads to overfitting. So you have too many features, you keep on splitting further and further. That works very well for our training data, but not for some random points. So yeah, it works better for low dimensional data. So I think that's it for. So now Daniel will be continuing with the other half of the session. Thank you, guys. And if you have any more doubts, you can still put it in the chat later on, and even in the WhatsApp group. I'll be always ready to answer.
Yeah, am I audible? Fine. I hope my screen is visible. So, hey guys, myself Daniel, and I'll be taking a session on ensemble methods today. So let's get right into it then. Okay, so these are all the topics which we are going to cover today. So the first one is going to be what are ensemble methods? Like, what do they exactly mean? So before looking at what ensemble methods mean in the context of machine learning, we'll try to look at it from a general perspective. Like, let's say if you guys would have been to any orchestras or any choirs, you would have noticed that this word ensemble has been used much more frequently. So why is it so? So when a collection of musical instruments which sound differently when played individually, are going to be, combined to produce a song that's going to be known as an orchestra. And these collection of instruments are collectively referred to as an ensemble. So the same idea is going to be applied over here in ensemble methods as well. Uh, so in the context of AI and machine learning, ensemble methods are nothing but a collection of small individual data models, which are, comparatively weaker. So what exactly weaker means? So weak learners are, a term which refers to models which have a lesser accuracy compared to several other models. And strong learners, of course, are going to be models which have comparatively higher accuracy. So the basic idea behind ensemble methods is we are aiming to combine those small individual weak learners to provide us with a stronger learner. So that is the basic idea behind ensemble methods. So yeah, if you take a real life example, say you're going to be a music composer and you have produced a song and you want to get a general opinion on it. So the most ideal case would be that you're going to gather some 60 to 70 people or even more than that, it depends, and you're going to get a general opinion from them. So why is it so? So this group might contain people who are very close to you and also people who are completely strange to you. So along with this, there is a very high
Daniel,
chance.
your screen is frozen.
Yeah, I'm still in my first screen. Uh, is it showing the water
All right.
ensemble methods slide?
It's
Yeah, yeah.
just showing the heading.
Oh, 1 second. I'll stop sharing and uh, is it visible now? Uh, is the presentation visible? No,
No, it's still blank.
blank. 1 second. How about now?
It's not for me. I think it's not for most of them.
Uh, and I'll try to rerun 1 second. Yeah, is it visible now? Does the heading say what are ensemble methods for you guys? Okay, yeah, fine. Let's continue then. Okay, fine. I'll start from the beginning then once again. So yeah, what are ensemble methods? I'll just go through it quickly once again. So, if we look at it from a general perspective, ensemble is basically where we are going to combine several, small individual inputs, and we are trying to maximize the output by combining the outputs from those individual learners. So, the same idea is going to be applied over here in machine learning as well. So, here we are going to be combining several individual small and weak learners which comparatively have a lesser accuracy, and we are going to combine those outputs to provide us with a better and stronger learner. So that is the basic idea behind ensemble methods. So yeah, and yeah, I'll provide you guys with a real-time example. So let's say you're a music artist and you want to get a general opinion on your music before publishing it online. So the best idea for you guys would be to combine, to gather a set of, say, let's say some 60 to 70 people and, get the opinions from them. So why is it better than just, calling out some 5 to 10 people? It's because your opinions or the criticism you will get from the people will be more diverse in this manner. Because the group might contain people who are expert in this domain, and it might also contain people who are novice to this domain as well. So you'll basically get a balanced view on this without having, some super specific opinion nor any, utterly basic opinion. So yeah, that's it about what exactly an ensemble method means. Now let's move on with why do we need an ensemble method? So the first and immediate reason we need an ensemble method is that it basically improves the accuracy of a model on the whole. So how does it do that? So you can think of those individual small weak learners as some, building blocks which capture the individual or unique aspects of a data set, which is not going to be captured by any complex model. So these individual small learners are going to capture those unique features. And when we are going to combine several such weak learners, we are going to, get the bigger and clearer picture of the data on the whole in a single model. So that's basically how the accuracy is going to be improved using the help of ensemble methods. So the next reason is ensemble methods are robust to noise. So I hope you guys know what noise is by now. So noise is basically just the random fluctuations in the data. So let me explain it to you guys with an example. Now let's say our ensemble method consists of some 100 individual models. Right. So among these 100 models, let's say three of them are affected with noise. So when we are going to combine the output of those individual models, when we are going to obtain the final output from these individual models, the contribution of those three individual models are going to be almost negligible because the noise itself is going to be negligible in those three models. Again, when we are going to average out the output for those 100 models, the contribution of noise to the final output is going to be much less and almost negligent. So this is basically how ensemble methods prevent the entry of noise into our data. So again, yeah, the prevention of entry of noise into our data is basically going to prevent, the chances of our model being overfit. So why is it so? I hope you guys know what overfitting means by now. If not, I'll explain it to you guys with a graph. So yeah, I hope this graph is visible for all of you guys. So as you guys can see, there are several tiny pink colored dots which are lying on this orange colored curve over here. That is going to be our data point. So this blue colored line over here
Daniel,
is
can
going
you stop for a minute? We are not able to see your screen.
oh, still 1 second. At which slide is it stuck?
Can you go back a few slides?
1 second.
I think it was stuck from the start.
Is it visible now?
Yes, it's visible. Can you start from the third slide itself? I think
One.
people were able to hear it. You can continue from the fourth slide.
You mean this one, right? Fine.
Yes.
Okay, so why do we need ensemble methods? The first and foremost reason is that they help in the improvement of accuracy on the overall model. So how do they do this? So the basic idea is that you can think of those individual model as some Lego blocks, and they will be able to capture the unique features of the data set on the whole, which won't be, which even the complex models won't be able to understand. So yeah, when we are going to combine these individual models, we'll be able to get a clearer and bigger picture of the whole data set, without having to deal with several different models. So that is basically how the accuracy is going to be improved with the use of ensemble methods. And the second reason is going to be the robustness to noise. So I hope you guys are familiar with noise by now. If not, they are just the random fluctuations which are caused in the data set. So I'll explain it to you guys with an example. Let's say we are having some 100 models in our ensemble method, and out of that, we are having 3 models which are affected by noise. So the contribution of the noise to the overall output, which is to say the final output, is going to be almost negligible, because we are going to just take the average, or we are going to take the majority voting of all those individual outputs as the final output. So basically, the effect of noise is going to be negligible. So that is how we are going to prevent the entry of noise. And yeah, ultimately, the prevention of noise from entering into our data is going to help us from preventing our model, be overfitting. So how is it so? I'll try to explain it with a graph over here. I hope the graph is visible now. Is it? Can you guys put it on chat if it's visible?
Yeah, it's visible.
Yeah, is it visible, right? Okay, fine. Yeah, these little pink colored points over there, along the orange colored curve are going to be our data points. And the blue colored line is going to be the ideal plot, which we expect our model to, accustom itself to. And the orange colored one is going to be obviously the overfitting line, and the green one is going to be the underfitting line. So as you guys can see, these points tend to be, fitting very much into the orange line. But in reality, it's because of the random fluctuations which are caused. As you guys can see over here, the model is supposed to be going, I mean, the data set is going to be lying along this blue colored line originally. But due to the random fluctuations, it seems to be more fitting with the orange colored line over here. So this is basically the idea behind overfitting. So yeah, so these random fluctuations which I've shown earlier are going to be prevented from entering into our data with the use of ensemble methods. So ultimately, it's going to result into the reduction of overfitting. So that is going to be a third reason. And the last reason is going to be the increased flexibility. So flexibility as in the flexibility for data scientists or the user, while the selection of models for any machine learning algorithm. So basically in ensemble method, you will be able to combine several different classification model at the same time. So that's another reason which improves the flexibility. So yeah, now let's look at the different types of ensemble methods.
Your
So
slides are still stuck now. It's stuck at the graph, the fifth slide.
is it 1 second?
If you're not able to do it, you send it to me. I'll share it, and you'll tell me when to change it. I'll do that.
Okay, fine. Yeah, I'll share it to you. 1 second.
Is the screen visible?
Yeah, it's visible.
Yeah, you were stuck here, and yeah, this is where you had to continue from.
Yeah, fine. Okay, so yeah, now we'll look at the different types of ensemble methods. So basically, we can classify the ensemble methods into three different types. The first one is going to be bagging. The second one will be boosting. So in this session, we'll be focusing mainly on bagging and boosting and their subclasses. Whereas there are several other ensemble methods as well, which are referred to as the advanced ensemble methods. They include stacking as well as blending, which are out of scope for the current session which we are taking. So yeah, uh, can you move on to the next slide? Yeah. So before getting into the details of those individual types of ensemble methods, we'll first look at the simple ensemble techniques. So what are all these simple ensemble techniques? Firstly, what is an ensemble technique? So earlier we have discussed that in an ensemble method, we are going to combine the output of several small weak learners, and we are going to obtain a stronger learner. So how do we do this mathematically? Like how do we combine these outputs? So that is going to be answered with these functions over here, or these techniques over here. So basically there are going to be three different ensemble techniques. The first one is going to be voting. Again, voting is going to be classified into hard and soft voting, which I'll explain in the next slide. So, and apart from that, we have averaging and weighted averaging. So what is the difference between voting and averaging? So voting is majorly used for classification tasks, which is to say where the outputs are discrete. And averaging and weighted averaging is going to be used in problems where the data set is continuous, or simply referred to as a regression problem. So that is the basic idea behind that. Uh, yeah, now let's look at the different types of voting. Uh, yeah. Yeah. So there are two different types of voting. The first one is going to be hard voting, and the second one is going to be soft voting. Hard voting is just simple. Let's take an example to understand it better. We are going to have a binary output, which is to say, let's say the output is going to be either 1 or 0. So we have three classification models. So out of those three classification model, let's say two of the models return the output as 1. So the majority is going to be, the majority vote is going to be for output as 1. So our final output is going to be just 1. Whereas in soft voting, it's going to be a bit more subtle. So here, instead of giving a straight answer, the model is going to give us with a probability of the outputs. So in this case, what we are going to do is that we are going to take the average of those probabilities, and we are going to consider which has a higher probability percentage. So from that, we'll be designing the final output. So as you guys can see, for output as 1, we have, the percentages as 70, 40, 90. So their average is going to be 66.6. And for output as 0, we are having the probability as 33.3. So our final output is obviously going to be 1. So these are all the simple ensemble techniques which we'll be using in, our upcoming ensemble methods. Now let's look into what bagging means. Yeah. Before understanding bagging, first we have to understand that bagging is not a single process. Bagging is basically going to be split as bootstrapping and aggregating. So firstly, let's look at what bootstrapping means. So bootstrapping can be thought of as a simple process where we are going to split the whole data set into several different subsets with the act of replacement. Okay, I hope you guys would have understood the initial part. But what about the latter part? Like, why do we have to replace the, data points once we have split it into subsets? I'll give an example for this. Let's say we are having some 5 red balls and 3 black balls. So let's split it into two cases. Firstly, we have to take one ball out of those 8 balls. Before that, we'll split it into two cases. Okay, so the first case is going to be where we are withdrawing 2 balls. Let's say we are withdrawing, 2 red balls. Out of the 5 red balls, we are withdrawing 2 red balls, and we are not replacing it. The second case is going to be where we have replaced both the red balls before picking the next ball. So the probability of picking a red ball in our first case is going to be, so since we had 5 in the first case, we have removed 2. So the probability is going to be just 1/2. And in the second case, the probability is going to be remaining the same as that of the initial case. So the probability of picking a red ball is going to be 5/8. So what does it exactly mean? It means that we do not want the probability of an individual data point getting chosen in either the first subset or the second subset to differ. We do not need any certain orderness while splitting this subset. We want it to be completely random. Therefore, we do not want any bias in the probabilities. So that's basically the reason why we are replacing the data points back into the data set before splitting it into another subset. So this is about bootstrapping. Now aggregating, as you guys would have guessed by now, is going to be the simple act of combining those outputs of the individual models. So there are two different images available on the screen right now. So if you look at the let's say the second one, which is to the bottom right corner, so we have, let's say, five subsets, and we are going to assign them to five individual models, and we are going to get five different outputs. So bagging is basically where we're just going to take these five outputs. We're going to combine them either with voting or averaging based on whether they are whether that is a classification problem or a regression problem, and from that we are going to get the final output. So that is it about bagging. Now we look into random forest, which is a special case of bagging. Okay, so random forests are basically normal, bagging algorithm, but here we are going to replace those individual, classification models with a decision tree. So firstly, let's address this. Why are we, implementing a bagging algorithm onto decision trees? Aren't they, more accurate by themselves? Why are we, implementing a bagging algorithm over them? So the reason is that decision trees usually tend to have a high variance, uh, which means they are more prone to be overfitting. So why is it so? It's due to the nature of decision trees to be usually, more complex and of more depth. So as Arjun was explaining, whenever we have a lot of features, the depth of the decision tree is going to be ever increasing. And again, in that act, we are going to there is a high chance that noise and any random fluctuation will be introduced into our data set. So that basically leads to high variance, and uh, you know uh, that basically makes the decision tree prone to be overfitting. So now we are going to mitigate this issue by implementing a bagging algorithm. How so? Because bagging algorithm, as we have seen, is going to be a completely randomized selection of subsets from a data set. So this introduction of randomness into our data is going to cancel out the complexity which has been introduced into the model by the decision tree. So this is basically how random forests are, random forests are going to be a better classification algorithm than decision trees. So let's look at it. Look at how a random forest works. So in the diagram given over here, we can see we have a data set which consists of four features and one target column. So firstly, we are going to select the features. So as you guys can see over here, the feature selection is going to be completely random. As you can see over here, the feature 4 has been selected thrice, whereas the remaining features are selected only once. So since the features are also completely randomly selected, again, this introduces another set of randomness into our data, again, which cancels out the complexity of the model. And yeah, apart from that, the remaining is going to be almost similar to that of a normal bagging algorithm. So now we are going to assign these individual models to a decision tree, and they are going to be processed, and the individual outputs are going to be, derived. As you guys can see, we have two yes and one no. So by major voting, we are going to obtain the final output as yes. So that's it about random forest. Uh, yeah. Now we'll move on with the slider quiz. Yeah, I'll give you guys 1.5 minutes to, answer this. Yeah, Arjun, can you stop sharing for a minute? I'll present it. If it's lagging, I'll share it to you.
Yeah, sure. Yeah, it's visible.
Yeah, it's visible, right? Fine. Uh, yeah, I'll show the results now. One second. Yeah. Okay. Yeah, most of the people got the right answer. Okay, we'll continue with the lecture then. Yeah, Arjun, can you please share the screen for the presentation? Yeah, thank you. Okay, before moving on to boosting, we'll look at a question. If a data point is incorrectly predicted by the first model and then the next and probably all the remaining models, will combining the predictions provide us with a better result? So the straight answer to this question is going to be a no. Why is it so? Let's say we are going to be having some let's say we are going to have some 50 models, and all the 50 of the models are going to predict a single specific record in an incorrect fashion. So even if we are going to combine those results, the final output is going to have that specific record as an error record. So the simple act of combining the results is not going to help us with the correction of error. So in these cases, what are we going to do? So that's where boosting comes into picture. We'll look at what boosting means now. Yeah. Okay, so what is boosting? Boosting is a sequential process where each subsequent model attempts to correct the error of the previous model. So simply put, you can think of it as a trial and error model, wherein the first model tries to classify the whole data set, and the second model tries to correct the error which has been committed by the previous model, and this process goes on and on and on. So how long does it go? That's going to be decided by the user, because the number of iterations is going to be a hyperparameter. So yeah, let's look at it in a pictorial fashion. So we have the first data set over here, the initial data set, which consists of 5 negative signs and 5 positive signs. Let's assign blue region to the negative signs and a red region to the positive signs. So the first classification is going to be a decision boundary, which classifies 3 negative signs rightly and 4 positive signs rightly, wherein it classifies 2 negative signs and 1 positive sign incorrectly. So the basic idea of boosting is that whichever data point is incorrectly classified, the weight of those individual data points are going to be updated as in an increasing fashion, so that the next model makes sure to classify those individual data points in a correct fashion. So the weights can be thought of as the probability of getting chosen by the next model over here. So since we have updated the weights for those individually, incorrectly classified data points, we can see that they are going to be classified rightly in the second model. And again, in the second model, we can see 3 negative signs are going to be classified incorrectly. Again, now their weights are going to be updated, and again, they are going to be classified correctly by the third model. Now when we are going to, now when we are going to combine all those individual decision boundaries, we are going to have a final combined classifier, which correctly classifies all those individual points. So that is the basic idea of boosting. Now let's move on and look at several different types of boosting algorithms. Okay, so the first one is going to be AdaBoost. AdaBoost is nothing but adaptive boosting. So it's almost similar to the normal boosting algorithm, except we are going to replace those individual classification models with a decision stump. So decision stump is nothing but a decision tree of depth 1, which is to say it only has one root node and two leaf nodes. So that is a decision stump. So let's look at the mathematical functioning of AdaBoost. So let's take a data set which consists of 3 features and one target column and 7 records. So firstly, what we are going to do is we are going to assign each of those records a sample weight. A sample weight, as we have seen earlier, weights can be thought of as probabilities. So the formula for a sample weight is going to make sense, because when we are going to add all the individual weights, we are going to get 1. So yeah, now that we have assigned the sample weights, the next step is to choose the decision stump. Uh, Arjun, can you move on to the next slide for once? Yeah, so the first step is going to be choosing a decision stump. So first thing we have to think about before choosing the decision stump is that which of those three features is going to have a least entropy. So let's say feature one has the least entropy over here. So feature one is going to be chosen as the decision stump. So once we are done with choosing the decision stump, we are going to have to calculate the total error. So let's say out of those 7 records, the third record is going to be incorrectly classified, which which I have highlighted over in the table. So yeah, so now the total error will be calculated according to a formula which is given over here, which is the summation of the sample weights of the errored rows or errored features. So since we only have one errored column, errored row over here, the total error is going to be just 1/7. And from this, we have to calculate the performance or say of the stump. So that is going to be given by the formula half log of 1 minus t by t. So yeah, it's going to be represented by neta. So neta will be getting a 0.896. So once we are done with all these calculations, so our next step obviously would be to update the weights. So how do we update the weights? So for an incorrectly classified data, the updated weight will be sample weight times of e to the power of neta. Whereas for a correctly classified data, the updated weight will be sample weight times of e to the power of negative of neta. So once we are done with calculating this, we are going to put it back into our table. So once, can you go to the previous slide? Yeah. So as you guys can see over here, we have included the updated weights column over here. And yeah, since we have seen that the weights are going to act as a probability, we want the summation of all those individual updated weights to result as 1. So what we are going to do here is we are going to normalize it. So after normalizing, we are going to obtain a set of specific normalized updated weights. And yeah, we are done with the calculations here. Now let's try to infer what it exactly means. So again and again, I've been iterating on a point. The weights are comparable to the probability. So to understand it more clearly, we'll try to write down the cumulative classes. So yeah, as you guys can see, for record 1, the cumulative class is going to be 0 to 0.086, and for record 2, it's going to be 0.086 to 0.172. And if you see for the third record, which is going to be our incorrectly classified record, the cumulative class is going to be 0.172 to 0.672, which is which has a class interval of 0.5, which is actually very high. It's going to be almost half of the total probability. So what it means here is that when we are going to provide this data set as a input for the second model, there is a very high chance that the second model will be able to classify this errored record in a correct fashion. So that's the basic idea behind AdaBoost. We're going to update the weights in such a fashion wherein we'll be able to correct the errors which have been committed by the previous model. So that's it about AdaBoost. Now we'll move on to gradient boosting. Yeah, so uh, yeah, so gradient boosting is going to be a supervised machine learning algorithm. I hope you guys are familiar with the term by now. So yeah, here the approach is going to be a bit different. What we are going to do over here is that instead of just combining all the outputs after correcting the errors, we are going to combine the predictions with the help of a hyperparameter. We are going to use the hyperparameter to scale those individual predictions before combining them. So how do we do that? So we'll look into that. But before that, why do we call it a gradient boosting? So the basic idea here is that the errors which are committed by those individual models are going to be minimized by moving in the direction opposite to the negative gradient. So what basically it means is that it's going to be just the implementation of gradient descent. And about gradient descent, we'll be looking into it in detail in the next session, optimizers. So yeah, that's going to be the basic idea over here. If you guys understand that, it's fine. So now let's look at the mathematical implementation of gradient boosting now. Okay, so now we have a data set over here, which consists of 3 features and 1 target column, which is income. From this, our first initial prediction is going to be the average of those income values, individual income values. and when we calculate the individual incomes, I mean the average of those incomes, we'll get the prediction as 3. So from this we have to calculate the error. So the error is going to be termed as residuals, and residuals is going to be obviously the actual income minus the predicted income, which I've listed over here. So now from all the data which is available to us, we are constructing a decision tree, and it will be looking something like this. I hope you guys would understood how to construct a decision tree by now. So yeah, once we are done with it, we can notice that in the leaf nodes we have more than two features or more than two residuals for that matter. So since we have to use those residuals for calculation, what we are going to do is that we are going to take the average of all those individual residuals present in that leaf node. So once we are done doing that, we have our final decision tree, which you can see in the second picture. So once we are done with all that, now let's look at the hyperparameter which I have mentioned earlier. So the hyperparameter alpha is mostly set as 0.1 in most cases. So as we all know, hyperparameter is something which the user has to fine tune. We have to fine tune it by ourselves, but initially we can set it to something close to 0.1 or 0.01. So now we'll look at the updation of weights. Uh, can you move on to the next slide? Yeah. So now how do we update the predictions? It's going to be given by this formula over here. Our new prediction is going to be the sum of old prediction plus alpha times of predicted residual. So this is what I meant when I said the predicted the predictions, intermediate predictions are going to be scaled by the hyperparameter. If you would have noticed, we would have just combined the inputs, combine the outputs directly in AdaBoost. Whereas here we are going to combine it with the help of a hyperparameter instead of just adding them directly. So that's the difference over here. So yeah, now when we update the dataset with the new predictions, we obtain something like this. And from that, we can again get the new set of predictions and new set of residuals. From that, we can continue the process till whatever iterations the user has specified. So once we are done with that, we'll be able to calculate the same for the training data set as well. We'll take an example to look at the testing data set now. Yeah, from the testing data set, I have taken up one record, which the actual income for that is going to be just 2.5. So now the model's task is going to uh, yeah, the model's task is going to be the prediction of the income for this specific record. So let's say the number of iterations has been specified as 4, which is to say we have 4 decision trees. So yeah, our initial prediction, as we saw earlier, was 3. And after that, we are going to combine all the intermediate outputs by scaling it with the hyperparameter, which is alpha. So once we are done doing all that, we'll be obtaining a value of 2.25, which is actually very close to the actual income 2.5. So this is the mathematical functioning of gradient boosting. So we'll move on. Yeah, there is a slider quiz for now. You guys can scan the QR and attempt it.
I'll stop sharing now. You share.
Yeah, sure. Oh, 1 second. I think I'm sharing. Okay, fine. Fine. Seems like most of you guys got the right answer. And for people who voted for option 4, uh, it's not exactly the right answer, even if it seems like the right answer. Because boosting, as I mentioned earlier, is going to be similar to that of a trial and error method, wherein the subsequent models try to uh, mitigate the errors caused by the previous models. So this sometimes leads to you know uh, a high variance or a overfitting you know scenario. So that is a reason. Fine, we'll continue with the lecture now then. Yeah, now we'll look at XG boosting. So XG boosting is nothing but extreme gradient boosting. It's almost similar to gradient boosting or normal gradient boosting, except that we have some extra parameters which help to enhance our normal gradient boosting. Extreme gradient boosting is generally more efficient and scalable than our normal gradient descent. Normal gradient boosting. It's due to the fact that we have a parallelization feature over here, which is to say that we'll be able to, parallelly compute. Uh, let's say we have a humongous amount of data, we'll be able to split it into several different subsets and run it on, run it by distributing them to, different number of CPUs or cores and, run them all at the same time. So that is what is meant by parallelization. So that makes the XG boosting algorithm more scalable. And the efficiency of this model is attributed to two salient features. The first one is going to be tree pruning. Tree pruning is nothing wherein, as the name suggests, we are going to be, removing some unwanted branches, which are the cause of introduction of random fluctuations into our data from the decision tree. So we can just prune out those branches from a decision tree. And regularization can be thought of as a penalty which can be imposed on the model whenever it's becoming more and more complex. Some commonly used regularization methods in XG boosting are L1 and L2, which you guys will be seeing in detail in the next session on regularization methods. So now let's look at the mathematical functioning of XG boosting as well. Yeah, the mathematical functioning of this is going to be almost similar to our normal gradient boosting, except that as I mentioned earlier, yeah, we are going to have some excess of parameters. So we can see something called similarity score over here. It's mathematically going to be represented as the square of sum of residuals. So we saw what residuals mean earlier. So yeah, and yeah, similarity score is going to be the square of sum of residuals divided by number of residuals plus lambda. Lambda is going to be the regularization parameter over here. So yeah, from this we can calculate the information gain. Information gain is going to be the similarity score of the parent node minus similarity score of the offspring node. So why do we calculate all this? The main idea is that if the information gain is going to be less than that of the pruning parameter, which is gamma given over in the in the last box. So yeah, if the information gain is less than that of the pruning parameter, we're going to have to prune the decision tree, which is going to be the basic classification model that is present in this algorithm. So yeah, that is going to be the only difference between gradient boosting and XG boosting. So yeah, that's it about XG boosting. Now we'll look at some different methods to evaluate the performance of ensemble methods. Yeah, I'll go through it quickly because it's not exactly very important. So metrics. So metrics is obviously the numbers which determine the performance of individual ensemble methods. There are lots of metrics like we have accuracy, we have R square score, we have F1 score, we have several other metrics as well. So they can be used to evaluate the performance of individual ensemble methods. And we have benchmarking. Benchmarking is basically the process where we compare and contrast, several ensemble methods together. And the last one is going to be cross validation. And one such cross validation method is going to be k-fold cross validation method, which you guys will be looking into detail in the upcoming sessions. So that's it about evaluation of performance. Now we'll go into the code implementation. Uh, yeah, thank you, Arjun. I'll try to share the code.
Try sharing. If it works, then fine. If not, I'll share.
Yeah, sure. Yeah, is it visible without any, fluctuation or something?
Yeah, it's clear.
Fine. I'll keep the code implementation short because we are going to just compare the accuracy which we can, obtain from each of those ensemble methods on the same data. We are just going to implement all the different ensemble methods without having to build each and every one of them from scratch. So yeah, the first block which you can see over here is going to be just importing of all the libraries and loading the data set over here. So the next block, we have the first command over here, which is going to print out several, uh, lines from the data set. Let's say some first 10 lines from the data set. And the next line of code is to, identify whether we have any columns or we have any columns with null values. I hope you guys are familiar with null values by now. So yeah, this line of code aims to identify the number of columns which have null values present in them. And the third line of code over here is nothing. It's just going to convert the data type of these three columns or these three features from a string type value into an integer type value, since we have most of the other columns in the integer data type. So yeah. So, and the next line of code is going to assign the values, assign the features except charges to X, which is the independent variable which we have over here, and Y is going to be assigned to charges, which is going to be the target column. And once we are done with assigning, we are going to split the whole data into training and testing using this function which we have imported from Scikit sklearn. So once we are done with all that, yeah, so now our first block of code over here is going to implement a linear regression over here. Yeah, you guys would be familiar with linear regression by now. So we are going to implement linear regression over here, the same set of code which you guys would have seen in the earlier session. So once we are done with all that, we can see we have an RMSE of 5796. RMSE is nothing but the root mean square error, which we'll discuss later. But yeah, and the R square score, I hope you guys are familiar with accuracy, but not R square square. So R square score is, very much similar to accuracy, except that it's going to be the counterpart for the regression models, whereas accuracy is going to be calculated for classification models. So R square score is going to be almost the same as, the accuracy, but for regression models. And that's the only difference. So we can see for the linear regression model, we have obtained a, R square score of 78 percentage. And now we are going to implement a random forest, regressor over here. And once we are done implementing, you can see the R square score has improved, and it's somewhere around 86 percentage over here. And now we have AdaBoost regressor over here, and the R square score for that is going to be 82 percentage. Now let's move on to gradient boosting regressor. So yeah, for this we have an R square score of 87, or around 88% for that matter. And when you compare it with XGBoost regressor, you can see the R square score for XGBoost is going to be 85, which is lesser than that of a normal gradient boosting. So why is it happening? Isn't XGBoost supposed to be more, efficient and accurate compared to a normal gradient boosting? If you guys would have had that doubt, the reason is going to be just simple, because XGBoost is going to be involved with a lot of hyperparameters which need to be tuned by the user. But as you can see from this block of code over here, I haven't specifically set any hyperparameters over here. I'll just let the model decide the default hyperparameters. So that is going to be the reason the R square score of the XGBoost regressor is going to be more than that of a normal gradient. I mean less than that of a normal gradient boosting regressor. So yeah, I think that's it for the code implementation part as well. So now I'll share the attendance QR. And meanwhile, if you guys have any doubts, you can unmute and ask. 1 second. Arjun, can you please share my presentation? I have the
Yeah,
QR
I'll do
code
that.
for here. Yeah, thank you. Oh, yeah. How do we calculate the value of the predictor value with which we are multiplying? Yeah, it's going to be a step-by-step process. Like we have an initial prediction over there, right? Which was 3 over there in that case. So the next prediction is going to be, the going to be something which we have calculated from the previous prediction, which is the old prediction plus alpha times of the, uh, you know, uh, alpha times of the residual. So we know the residual and we also know the old prediction. So the new prediction we can calculate from that. So that is going to be that for the first iteration. And for the second iteration, we can obtain the new prediction by calculating the sum of the obtained the obtained new prediction for the first iteration added upon with the uh, multiplication of alpha and that of the residual from the first iteration. So that's how we calculate the predictor value for second iteration. And this process can be kept on going.
Also, if you've already filled the first Google form that was showed earlier, then you don't have to fill it again. You just have to fill one form in a day. And if you guys have any more questions, you can ask. Until then, the form will be open. You can fill up your attendance. Yeah, if you fill the form, you can leave.